Welcome to our presentation, Search and Evaluation Methods for Class-Level Information Retrieval. Our work is about extended use and evaluation of voting techniques applied in expertise retrieval. Voting techniques are one of the approaches used in the expert search task. This approach takes a search query in order to retrieve documents which vote for their author as an expert. We apply selected and varied voting techniques for a more generalized search for classes of documents. Further, we introduce two automated evaluation methods which allow us to evaluate a huge number of queries and its found class items. Given a query against the collection, we want to find the best matching class CX, respective a ranking of the best fitting classes. Documents of one class have the same color. This takes two steps. First, the similarity search on document level, where we derive a document ranking. Second, applying voting techniques to get a ranking on class level. Each document votes for its related or associated class. The class-level oriented approach searches on document collections containing documents that can be classified by properties or metadata. Collections can consist of web pages, which then are organized or categorized by their companies. C1 to C4 would represent companies, and the small characters stand for their belonging web pages. Another example could be articles, which are classified by the journals they are published in. C1 to C4 would represent journals, including their articles, represented by the small characters. In this second section, we describe the applied voting techniques. For a ranking on class level, first a search on document level is done. In this paper, we get a ranking by applying the BM25 scoring function. The resulting documents vote for their class, in our case for their journal. Applied voting techniques in this paper are demonstrated next. Known from literature, CumSum top n takes the voting scores into account, but only to a certain rank per class. In this slide, n is set to 2, only the first two scores per class are considered. Also a known voting technique is the reciprocal rank, which is purely based on the document ranking and not on the scores. Newly introduced in this work is the exponent x, which allows us to fine-tune this approach. Per class, all reciprocal rank values are summed up to derive a class ranking. In this example, the basic variation having 1 is demonstrated. This next technique uses RR powered by X as a damping function for the document scores. CumSum RR powered by X is newly introduced in this paper. All document scores are provided with a damping function in order to emphasize the upper ranks per class. They are summed up for each journal and finally determine the class ranking. The technique XCumSum RR powered by X strongly emphasizes the upper ranking document scores. The damping factor is the same as in the example before, but the document scores are taken in the exponential form. Votes as a classic voting technique just counts the number of documents for each class as voters. As we can see in this example, the orange class, which has been on the last ranking level before, this time has the maximum score in the class ranking. The last applied technique in this paper is CompMax. It only takes the maximum score for each voting document per class into account. We come to section 3, collection and setup. The experiments in this paper are based on the A- collection, reduced to journals for which the title, abstract and full text is available. We sent 10,000 article titles, randomly selected and removed from the collection, as search requests. The index is searched on titles, abstracts and full article texts. Each request yields a document ranking. This is the step of similarity search on document level. Then the voting process determines the ranking of the journals. For evaluation, we determine the rank of the requested article's journal. This table shows the results for the search scenarios: search over titles, abstracts and the full text documents. The mean reciprocal rank is taken as an evaluation measure. It results from the rank of the first relevant answer. This relevant answer is the journal from which the query was taken. Green values indicate good performance, going over white to red values, which stand for poor performance. Techniques emphasizing the first ranked voters yield better results over all scenarios. Our newly proposed techniques, marked in yellow, yield strong competitive results. Our next goal was to evaluate the relevance of other ranked journals. Therefore, we calculated thematic relationships between the journals. These grades of relationships are based on the intersections of common authors publishing in the journals. This table shows the results for the search over titles at position 1. Again, green cells show good performance, a high relationship with our desired journal. White and red cells show decreasing performance. The first quartile shows the minimum grade of relationship for the top 25% of the ranked journals. The median indicates the grade for 50%. 75% of the journals have a grade equal or better than the figure shown in the third quartile. Again, our newly introduced techniques show very good results. CumSum RR, exponential variant of CumSum RR, and RR powered by 3/4. Our next question is if voting techniques prefer journals dependent on their size. Therefore, we separated the journals to bins of different journal sizes. The lower bins include small journals, the upper big journals. Each graph indicates the number of top 1 ranked journals per bin. An unbiased result would be on the dashed line, which reflects the origin of our requests. Looking at the green line, which performs best, it turns out that techniques moderately preferring big journals and neglecting small journals perform best. That's it for our presentation. Thank you for your attention.